Welcome everybody to the Research Methods Community Doctoral and Junior Faculty Consortium. Today is our first session. It is on the very topic that has been gaining a lot of interest in the recent years, right? Natural language processing and machine learning. So we have an absolutely fantastic lineup of the panelists. We have Raj Choudhury from Harvard, we have Ariana Marchetti from INSEAD, and we have Maciej Workiewicz from ESSEC, and all very, all experts in both NLP and ML topics. I also want to give a shout out to Anja Kmine. She is my fellow co-organizer. Unfortunately, she had an overlap, so she will not be able to be present with us live today, but she has been doing a lot of work behind the scene leading to this event. So to put things in perspective, the idea of this doctoral and junior faculty consortium is to provide an introduction to the methods which are of particular interest, or to any topics which are related to research methods which are of particular interest. This is our first session, so to put things into perspective, we will have two more sessions. We'll have one on Wednesday and one on Thursday. On Wednesday, we'll be talking about the two-sided matching methods. And on Thursday, we'll be talking about the formal models. So again, if you're interested in learning about research methods, if you like our session today, again, you're very welcome to join the other ones. Now, back to today. Today, we have this very interesting session on NLP and machine learning. So how we will proceed? We will start with the panel session. So we'll have all three speakers present on the topics related to our overwhelming theme. So Maciej will start with an introduction to what machine learning is and give us a bunch of insights. Then Raj will talk about supervised machine learning, and then Ariana will talk about topic models. So we are switching more into the NLP area. And after that, we'll have the Q&A. Then around 12:15 mark, we will have a little break. So those of you who have registered for the breakout room, or even those of you who have not, but after seeing all the speakers would really love to talk to them, please stay connected. During this little break, I will assign you to the breakout room. So when you come back, the magic will be done and you will be with the speaker of your choice. Okay. So in terms of the virtual etiquette here, the way we'll do the question is please post them in the chat. I encourage you to start posting questions already during presentations. I also encourage the speakers to start engaging with answering those questions. Once we do all three presentations, I will call on the questions that either based on chronological order or based on something that has garnered a lot of attention. So we will bring that into the live discussion. So we'll probably have around 15-20 minutes for the Q&A. So again, please start posting questions in the chat. We will all come back to these later. And I think at this point, I've done my job as master of the ceremony. Well, I also have the unpleasant task of being the timekeeper. So yeah, we'll have between 15-20 minutes per speaker, and I'll have to be the bad guy to interrupt you and say we're out of time. But other than that, I think that's it. So without much further ado, I'm gonna stop sharing. I'm gonna pass it to Maciej. And also because Maciej is super savvy in all the technology, he has a special way of sharing his screen. So please make sure that right now on Zoom, you have the view set to the speaker. So this way you can see Maciej's screen in full. So please set to the speaker. And with this, Maciej, the floor is yours.
Okay, thank you very much, Elena. And Anne, thank you for organizing this. I think it's a great initiative. And welcome everyone to this session and workshop. So my name is Maciej Workiewicz. I'm an associate professor at ESSEC Business School in France. And today I'm going to talk to you, sort of provide a gentle introduction to machine learning. Sort of now my credential in terms of how I got sort of into those methods is in my research, I do a lot of computational modeling, which includes complex adaptive systems and reinforcement learning. And as you will see kind of quite soon, this sort of algorithmic approach to sort of modeling reality is really where machine learning comes from. Kind of its common root, or kind of its origin really lies in the sort of science of cybernetics, which sort of developed in the 40s and 50s. And later on also became sort of the foundation for the behavioral theory of the firm. I mean, for those of you who are kind of theory nerds, the origins of AI and behavioral theory of the firm, the Carnegie School, are pretty much the same. Kind of, it's cybernetic. I also teach a class on machine learning for researchers. In the doctoral program. I've been doing this since 2019. So kind of, over that time, I sort of developed a set of kind of key ideas, and introduction to how we can use those incredibly powerful methods to help us in doing our research, regardless if these are experiments, sort of empirical panel data and other. So without further ado, sort of my technological prowess has been already announced, which means that now everything will go wrong from this point on. But let's see how far we can go. So I'm going to now switch to this presentation mode. So make sure that you have the speaker view so you can see kind of a big image because I'm going to sort of present everything in the same camera feed. So I'll just give you a few seconds to press a few buttons in your Zoom and then we will proceed. Okay. So I kind of have a semi-ambitious plan here. We have about 18 or 17 minutes now to cover a few things. So generally, I wanted to talk about what is machine learning, kind of some basic understanding of it. What are the three main categories of machine learning algorithms? And then I'm going to move into sort of the logic behind machine learning, because what I've noticed is that people who come from more kind of empirical methods, there is kind of a little bit of a shift in focus and in emphasis on some parts between the sort of statistical approach and algorithmic approach that machine learning is. And then I'm going to also talk about some of the applications of machine learning in academic research. I'm not going to go too deep because my two other esteemed colleagues will sort of go in a greater detail into some of the methods. But this is kind of going to be a high-level overview. All right, so what are we talking about? So machine learning is sort of part of a larger field of artificial intelligence. So you can achieve artificial intelligence with machine learning, but you can also do it with other methods. So kind of machine learning is part of that. If you have heard about deep neural networks or neural networks, this is, again, a subset of machine learning, is a particular class of models that have special sort of features. But there are many, many more models than just kind of neural networks. And actually, from our point of view as researchers, very often those, let's say, less advanced non-neural network models are really where a lot of our sort of tools are. And I'm going to also explain the reason why. So first, kind of let's try to think about what really machine learning is. If I sort of gave you sort of a set of some kind of data points and told you to fit a line that kind of best sort of fits here this particular data, but then told you that you cannot use OLS or any sort of linear regression that you have learned in your basic econometrics, sort of in that case, you would have to kind of come up with a different approach on how to fit a line if you kind of suddenly forgot or didn't have those tools. If I were to ask you to come up with an algorithm on how to fit a line into this data, you might come up with something like this. So starting at the top left, what you can do is you can pick a polynomial. I mean, here I ask you to fit a line, so you would just kind of choose a linear sort of a model. It's kind of a simple line. So you have two parameters, intercept and slope. Now I would also ask you to choose some cost function. Now by cost function, I mean you have to choose some measure that tells the algorithm how far you are from the goal. If you remember sort of from OLS is using the mean squared error. So it kind of calculates the squared errors from the prediction to all the other observations and tries to minimize that particular value. So why don't we just take the same cost function and we're gonna sort of build an algorithm that is trying to minimize it. Then we're gonna set some initial values for the parameter. Here we can choose, for the slope and the intercept, we can choose any value we want. We can choose randomly, or we can just choose something that kind of looks okay. Once we have those initial parameters, we're gonna kind of build a loop, like a kind of an algorithm that proceeds in the following way. So we select those initial parameters for the intercept and slope, and then we go and iterate. We basically wiggle those two parameters. So we change the intercept and slope a little bit. And then we see if the mean of squared errors now has gone down or went up. And we want it to go down, of course, because we want to minimize the mean squared error. And we can do it basically either randomly, we can come up with more clever algorithms, but even in the most kind of the simplest way, when we just kind of select a slight deviations from the status quo, we can go through this loop over and over again. And as you can kind of, would probably expect is with time, given enough computational power, enough cycles, the algorithm will actually start to wiggle this line and move it towards the optimal fit. Now, here you can just trust my word for it, but I can also send you the Python code for exactly this algorithm. With enough iterations, you would actually almost exactly approximate the OLS line. You'll have this kind of a simple, kind of like a random sort of walk trying to minimize this mean squared error. And lo and behold, using very simple algorithmic approach, kind of a slow evolution of this function, you would actually achieve what otherwise you would need the whole OLS for. Now, this may not sound very impressive. It's a very simple function, but believe me that kind of the same logic of kind of looking for the best fit, kind of trying different approaches is really what underlines the machine learning. And that's kind of like one of the major sort of logical principles in machine learning is sort of trying different things, finding sort of a clever algorithm that can sort of minimize the cost function and give you the best fit. Of course, your goal may be different, and I'm going to describe it in a moment, kind of different types of things you can do with this simple logic. But that's a very important idea to keep in your mind as we progress. Now, the mean squared error, this kind of very simple cost function, is also the most used cost function for a whole family of machine learning models. So actually the neural networks that we usually use and are very impressed by also use the mean squared error. I mean, the whole idea of backward propagation is to train the neural network in such a way that you're going to minimize this particular error. So this logic that we just kind of discussed with this simple linear algorithm actually carries through the whole family of machine learning models. Now, the three main families in machine learning kind of can be split into the supervised learning. So this is kind of tasks like classification, regression, prediction, unsupervised learning, which is using machine learning to kind of discover hidden structure in the data, and reinforcement learning, where we kind of train the model by giving it rewards or punishments for the tasks. Now, I'm going to kind of click a button and you're going to see a lot of different models because, as you may expect, machine learning has been kind of a popular thing recently. So a lot of people have been doing a lot of things in all of those different sort of three families. So we have a whole kind of plethora of models of basically different types of algorithms that kind of try to solve a particular task. So we can do regression, we can do classification, we can do non-parametric learners that help us to predict things. That's the supervised learning. We can do clustering, dimensionality reduction. So for example, large kind of natural language processing would fall into that particular family. These are kind of another type of models. And finally, reinforcement learning. Now, reinforcement learning, up until very recently, we didn't use a lot in our academic research, but ChatGPT is actually a model that uses a lot of reinforcement learning logic, both in the design of the model and also how we interact with it. Okay, now one very important thing. So the second thing that I want you to understand after sort of this algorithmic approach is that there is no free lunch in machine learning. There is no best model that you can sort of ex ante say, okay, I'm going to use this model because it's the best for what I want to do. In machine learning, what usually people do is they have a task in mind, like let's say they want to predict something, and then they will try multiple models and try to see which one kind of does the job best in terms of the accuracy of prediction. Sometimes it's the speed sort of that we want to achieve. But because every model, kind of every algorithm has a little bit different logic. So some of them try to kind of wiggle a line or a set of kind of lines or a multidimensional polynomial. Some of them are sort of trying to divide the parameter space kind of with sort of binary yes or no questions. You cannot really specify ex ante which model you want to use. So in machine learning, you want to try a lot of them before you actually decide which ones will actually fit your task the best. So that's the second part, no free lunch. Now, the different models in machine learning also differ in terms of their sophistication. And from our point of view of someone who does research, sometimes what you also want to know is how does the model really determine the right answers, right? So for example, with prediction, you want to be able to tell which variables in machine learning, we call them features. So which features have actually been the most useful for the model to make the prediction? Now, some models will give you this, some models won't. Some models also, the logic will be quite easy to tell. So for example, like linear regression or logistic regression or regression trees, decision trees are easy to explain to your reviewers, right? If they, for example, ask you, how did you determine that this company, let's say, is, is sort of doing good R&D, you can actually say, okay, here are the features that actually the model is using to predict it, right? And you can then sort of theorize, or you can kind of argue why this is a good selection. However, some models like support vector machines or neural nets will not give you that. Basically, it's a black box, and all you can do is wave your hands a little bit, and kind of say like, hey, listen, this is what I do. I get a good prediction. Some other people maybe did it this way. But it's kind of you lose this sort of ability to kind of see through the logic of the model. So this is also something to keep in mind. That sometimes something most powerful and most advanced may not necessarily be the best from the point of view of doing research. Sort of you want to be able to defend it. Now, the third point to remember about machine learning is that usually what we struggle the most in applying those methods is because we are not really limited by the kind of complexity of the model. We have to be very careful that the model doesn't get too clever, kind of too complex, and will basically start to overfit the data. But also that the model is not too simple, right? It actually leaves something on the table as kind of being too crude. So this balancing between kind of the model that is too dumb or kind of too clever is very important in machine learning. It is called the bias variance trade-off, and kind of here you have a nice illustration what I mean by kind of either a model that is too simple, right? So we are trying to fit a linear model into data that is, clearly sort of not really linear, or maybe we are sort of trying to overfit by really kind of hugging all of the observations very, very well. Now in machine learning, the people have developed two strategies to deal with this problem. One is cross-validation. So what you do in machine learning, you split the data into two data sets, kind of two sets. One is the training one, on which you train the model, right? You develop the model kind of, is being trained and sort of learns from the observations. And then you use the other set of data to test the model. It's basically like, giving your students prior exams to learn, but then you test them on a new exam, right? So you want to check if they really understood the principles or just memorize the answers, right? Of course, you want the former, not the latter. And another one is regularizing. Regularizing in machine learning is imposing a penalty on the model so that it cannot get too clever. Basically, it's kind of there's a penalty for adding an additional level of into a decision tree, like adding more branches, or you want to apply some breaks into those models, which otherwise would really try to hug the data as closely as possible. Now, what are the right levels of regularizing? Well, you try and you see which ones work best. That's basically the answer. In machine learning, it's the really outcome or the sort of effectiveness of the model to either predict or to sort of categorize, to cluster that really matters, right? There is not really kind of an kind of ex ante sort of decisions that you make. Kind of the proof is in the pudding. Now, the reason for this is that there is a fundamental difference in terms of how the algorithmic approach of machine learning and the statistical approach. So when you think about the origins of the two approaches, statistical approach comes from mathematics, whereas the algorithmic approach comes from computer science and engineering. If you are doing sort of econometrics, what you're basically trying to do is to fit your theoretical model that you have theorized for, right? So you theorize for, let's say, a linear model with a given set of variables. And then what you're trying to do is you try to see if the data support your model. You're trying to estimate if the parameters, sort of the betas in your model, are statistically significant as predicted in the predicted sort of direction. So that's your interest. Now, if you're doing machine learning, what you really only care about is the prediction. It doesn't really matter what's on the right-hand side, right? If it's a support vector machines, decision trees, or neural net, it doesn't really matter. As long as you get a good prediction and you sort of confirm with the cross-validation, that's really all that matters, right? So that's a very important also point that we cannot use machine learning to substitute for statistical models, because you cannot prove or estimate or get significance for any of the parameters with machine learning. It's a completely different task that you are kind of that you undertake. Okay, so now how does machine learning fit into all of this? So here's my kind of a toy model of the scientific method, at least as outlined kind of by Isaac Newton. So the idea is that initially you look into the real world, you see something interesting, you start to theorize, you form hypotheses. So if I'm right, then if this happens, then that should happen, and so on. And then you kind of go and you test the theory, and you either reject or fail to reject, and boom, and you have a paper, right? I mean, that's like the ideal world. So where does in this scientific method machine learning fall? Well, first, what you can do is you can use especially unsupervised learning to kind of look and find hidden structure in the data. So you can look at sort of some big data sets and kind of try to see, are there which variables in this huge data set, let's say, predict something? And you can kind of see, oh, here are the variables that I would never kind of come up with. I wonder why this is so. Of course, then you have to collect the different data to test the hypothesis that you formed this way. But the idea that actually you can use machine learning to see more in this world, I think, is very, very powerful. And I think now increasingly with the large language models, it will become really kind of quite a big source of ideas for us. The second part is theory testing. So here, what we use machine learning mostly for is to create new variables. This is what machine learning is really good for. So previously, things like photographs, large amounts of text were really beyond our reach. We would either need a lot of people or a lot of time to go through this type of data. Well, today, with the help of machine learning, we can do really a lot. So this really kind of saves us a lot of time. So creating new variables is a big help here. And I think one of the kind of most useful uses of machine learning up to date. And finally, I would say, since November last year, we have another use for machine learning in research. So I don't know how many of you have been playing with large language models like ChatGPT, but it can be your research assistant. It can write computer code for you, even if you don't know Python, and suddenly you can acquire this ability. It can be your copy editor. It can be your data analyst, and probably more and more as we go forward, and new iterations of those large language models are appearing around us. So it's a really super powerful tool, which I think is kind of changed the game quite significantly beyond just supervised and unsupervised learning. So one word of caution, however, with large language models, so this is kind of my little meme here. When you use them, don't trust and verify. They are very, very powerful, but they can get you into trouble, right? So if you don't know what you're doing, if you have no idea kind of, how to verify whether the sort of output of those models is correct, so it's better not to touch it, right? Because kind of it's like a calculator that 99% of the time gives you the right answer, but then every 1% of the time it gives you a completely wrong answer, right? If you cannot tell which one is which, well, then bad things can happen. Now, here's kind of a list. I'm not going to go into detail through this, but there's a lot of different applications of machine learning in academic research, processing images, processing language. So it's kind of a big bodies of text, annual reports, emails, you name it. You can now do, there's lots of free off-the-shelf open source tools to do this. You can also use it in traditional econometric approaches, like, for example, in the first stage of instrumental variable estimation. You can also check if your experiment worked, because you can, for example, see if you can predict from the outcomes whether someone was in the treated group or control group. You can test the theories, when you see your adjusted R squared, you can use, let's say, random forest and see, okay, if I was not limited to my theory, how much of the variance in the dependent variable could I explain, if I just kind of did a complete sort of brute force machine learning prediction exercise. And finally, you have your almost free research assistant. So a lot of cool things. I will just leave you with this one kind of image. I really like it. You can go to the website. It's a Python machine learning open source initiative project where they kind of make it available to researchers, all of those very powerful tools. And they have this kind of handy kind of algorithm to finding the right algorithm, right? So you can kind of see what you need, and then depending on the quality of data, what you want to do, you can sort of find a good starting point for your machine learning adventure. So thank you very much. I'm going to stop here, and I'm going to let my other colleagues to continue. In the meantime, I'm going to check the chat, and I will be here for the Q&A and the breakout rooms. Thank you.
Thank you very much again. Great introduction. Thank you very much. There are already some questions in the chat. So please, again, I encourage you, go ahead and start engaging the conversation. So this is also the moment where you can switch back to the gallery view instead of the speaker view. And I just want to still give that shout out. That was really cool technology. So now, after Maciej gave us this excellent introduction to different methods and what machine learning is, so Raj, I assume you're going to talk in much more detail about the specific type of machine learning, the supervised models. So again, the floor is yours. Go ahead and share your screen.
Yeah. So thank you, Elena, for organizing this, for inviting me. And Maciej, that was a great presentation. I can't match your technology, but hopefully I'll build on what you said. So there'll be some common themes in both what Maciej said and what I'm going to say. So my name is Raj Choudhury. I'm an associate professor at the Harvard Business School. And it's great to be on this awesome panel with Ariana and Maciej. So I'm going to, like Elena said, I'm going to zoom into the world of supervised machine learning a little bit. And specifically, I'm sorry, let me share my screens. The slideshow, not the slides. Can you guys see the slides? Yeah.
Yes. Perfect.
So I'm going to zoom into the world of supervised machine learning a little bit and specifically talk about this paper, which was published in SMJ, co-authored with my doctoral student, Ryan Allen, and with Michael Endres. And this presentation is something I use with my doctoral students in the doctoral seminar here. And I presented this in a few other occasions. So some of you might have seen this earlier, so apologies if that's true. But I'm going to try to build on what Maciej said for folks who are relatively new to this world of supervised machine learning. So I guess the first thing I'll say is that the use for a supervised machine learning, as Maciej said, is to shed new light on data, and specifically to shed light on potential nonlinear relationships between variables that might have gone unnoticed. Now, the first thing I'll say as a caveat is, do we need machine learning to shed light on nonlinear relationships? We could, for instance, run regressions with all kinds of nonlinear terms on the right side and interaction variables, and we could potentially do a very exhaustive job. But I would argue that supervised machine learning methods provide us with another tool and something that's really fast and something that can shed light on relationships that might go unnoticed or the researcher might miss. I think Maciej mentioned this, and it's worth repeating. So to the best of my knowledge, we still don't have a way of establishing any causality with these methods. So we are in the world of induction. We are in the world of exploring patterns in the data. And then once we have noticed those patterns in the data in an inductive way, then we can develop hypotheses around them and deductively test them, either in a different paper or maybe in the same paper but with lots of transparency. We should always position these methods as an inductive pattern searching exercise, not a causality nailing exercise. So I'll probably come back to this table at the end. So this is the study that we use in the SMJ paper to motivate these methods. And this is a study of attrition, of turnover of employees in a large firm. And so if you just looked at the turnover probability as a dependent variable, and you ran a regression with lots of things that you might think might predict turnover, one of them being the training performance, the score that the workers received during a mandatory training program, then the naive model, and I'm calling it naive with a lot of humility because you can achieve what machine learning does with lots of iterations, I guess. But at least the naive model predicts a negative correlation between training performance and the probability of turnover. Now, what pattern is missed in this analysis is that there is actually a very interesting nonlinear relationship between the performance in training and the probability of attrition before and after the first 6 months of the employee's tenure at this firm. So indeed, before 6 months, there is a negative relationship between training performance and leaving, but after 6 months, that relationship turns positive. So after 6 months, the people who received high performance scores in training, they are more likely to leave. So the story then becomes more nuanced, where the firm is able to use the training exercise as a sorting mechanism, finding the left tail of the distribution, but the right tail of the distribution actually take advantage of the training, and then they are more likely to leave. Now, that is a completely different a deductive proposition compared to training performance leading to more or less probability of leaving ex ante. And so this is the pattern, the nonlinear pattern, what happens before and after the first 6 months that goes unnoticed in a very, very naive regression. And that is what machine learning in our case helped us pick up. Now, how did we do that? So I'm going to jump into the methods themselves. So Maciej talked about the bias variance trade-off. Just to reiterate, the way supervised machine learning works is that you have a training data set and you have coded some variable there, in our case, attrition or turnover, and you're trying to predict which variables predict attrition in that training data set. Now, if you perfectly predict turnover in that training data set, then you might risk that the model you have developed in making that prediction may not work so well in an out-of-sample prediction. So that is the bias variance trade-off. Now, on one hand, we want a high degree of predictive probability in the training data set, but we also want the model to predict whatever we are predicting, in our case, turnover, out of sample. So that is why it's important to ensure that we are able to develop a model that holds its ground in the training data, but also outside of the training data. So that is what the bias variance trade-off is pointing to. And I think Maciej mentioned this. I'm going to go a little more deeper. There are two methods to do that. One is called cross-validation, and the other is called regularization. So what is cross-validation? In cross-validation, you are initially, at the very onset, you are leaving out some part of the data to test the model later on. So you develop the model using the training data, but you leave out some part of the data that you're going to take the model to at the end of the exercise. And then you're going to estimate how well that model predicts the outcome variable of interest in the out of sample prediction exercise. So there are lots of ways to do cross-validation. The most common, one of the common ways is known as the K-fold cross-validation method. So what is the K-fold cross-validation method? You partition the data set into K partitions. You use K-1 partitions to develop your model, and then you test the model in the Kth partition. And you can do that iteratively. You can develop, you can choose K partitions over many, many iterations in almost a Monte Carlo simulation fashion. So that is what the cross-validation method is. The regularization method is trying to avoid the problem that you're predicting, your model predicts perfectly in the training data. So for that, there are many ways to do that, and I'll go along as I develop. As I tell you about the different supervised methods, I'm going to tell you how regularization is achieved in each one of them. But before I go into the specific algorithms to develop the model, so once again, just to take a step back, there is data. We have the training data. We have left out some data. We're trying to develop a model that predicts an outcome, and we're going to use multiple algorithms to develop that model. So we are going to, first of all, pre-process the data. We are going to select a number of algorithms, and I'm going to show you 3 of them. I'm going to show you the decision tree algorithm, the random forest algorithm, and the neural net algorithm. We're going to choose how to regularize in each one of these algorithms. And then we are going to, of course, do our cross-validation step, which I explained earlier, which is to test the model in the out-of-sample data. And then we are going to assess the loss function. So Maciej talked about the cost of this prediction, and that is essentially the loss function. We're going to evaluate the loss function in both our training data set and the out-of-sample data set. We're going to try to interpret these models. I think I saw a question in the chat on how to interpret these models, and I'll talk about that. And then we'll repeat everything multiple times with multiple algorithms, but also multiple hyperparameter values within each algorithm. So I think Maciej mentioned this. I'm going to reiterate this both now and at the end, that in using supervised machine learning models, it's imperative that we do robustness. Just like we do a bunch of robustness checks with econometrics, it's very, very, very important to ensure that the patterns we are finding are robust to multiple algorithms, multiple hyperparameters of the same algorithm. And there's an entire table in the SMJ article that we wrote on how to do robustness. And I say this because many of us are now reviewing these machine learning papers, the papers that use machine learning methods. And both the authors of these papers, but also the reviewers, need to hold these papers to the same high standards that we hold our regression analysis to. So in case you are wondering how to hold the robustness check, once again, I'll make a shameless plug. Please read our SMJ paper. We talk about that in a lot of detail. So the first algorithm I'll talk about is decision trees. So let's see where we are. We are working with a training data set. We're trying to develop a model that predicts the probability of turnover. That's the example I'm working with. And what the decision tree algorithm does is it just iteratively partitions the data set using a combination of variables where the loss function is minimized across the two partitions. So the first route, you can see what the algorithm has determined is that if training performance is below or above 3.995, and why 3.995? Because the algorithm has gone through many iterations, then the two partitions you get in the data, they minimize the loss function. So that's the first cut of the tree. And then the algorithm is working with the left branch and the right branch and iteratively cutting the data into two partitions in each stage. Now, we talked about regularization. Once again, what is regularization? It's a method to not overfit the training data. The way to do regularization in decision trees is very simple. It is to have a stopping rule saying, I'm not going to go to the next step beyond 3 steps or 2 steps or 4 steps. So you can cut off the tree at a depth of 3 or a depth of 4, or you can set that hyperparameter, and that is the regularization hyperparameter for a decision tree. You can specify the depth of the tree. So that's a very easy way to do the regularization. I love this method because it's very visual. You can see the entire model in front of your eyes. So in this case, the model is the nonlinearities first with training performance. Then on the left side, it's the tenure. The right side, it's the tenure, and so on and so forth. You can visually see the model, and this is good for transparency. Imagine I'm using a supervised machine learning model to determine whether to give someone a bank loan or a credit. Then I can take this model to the consumer and say, this is the model. This is the visual representation of the model. So it's very transparent. The next set of algorithms are related to these random forests. What are random forests? Just like the name suggests, it's an ensemble of trees. So you run the decision tree over and over again, and then at the ensemble level, you are making some average prediction, either through some voting mechanism or some simple average rule. Once again, you can regularize this very easily by specifying the depth of each tree. So that's what random forest is. The third one, I'm going to skip many others. I'm just going to focus on the 3 models. The third one is neural nets, and Maciej already showed you a picture. This is very computationally effective for large samples of data. A neural net is very conceptually, it's very simple. It's a collection of steps where in the first step, you have a linear combination of the data on the left, and the next step is a nonlinear combination. So it's a linear, nonlinear, linear, nonlinear sequence of combining the data on the left. Now, the typical nonlinear functions that are used are either sigmoid or ReLU. ReLU is something that's very commonly used. It's and then the final nonlinear step is always a sigmoid step. And then Maciej talked about backpropagation, which is how I know how to improve the model. So once I've seen the prediction, I can compute the loss function again. And if the loss function is not according to my benchmarks, using backpropagation, I can keep going. I can either add more linear, nonlinear steps, or I don't have to join each step in the middle of the entire neural network. So the way to regularize a neural network so that you don't overfit the training data is to have some missed connections. So you don't have to use every input in every step. So you start with a bunch of inputs, then you have a linear step, then you have a nonlinear step.
I got was basically there is no data, right? There's no data.
I'm sorry.
Yeah, like if somebody is, would you please like mute yourself except for the speaker so we don't get any like interruption?
No worries, thank you. So the way to regularize is to have some missing connections. So you're not joining all the inputs of the previous step into the next step. That's how they regularize a neural net. So I'm probably a little behind on time, so I'll skip this. This is also a table from the SMJ paper, which talks about how you go about selecting the right algorithm for your application. And we talked there about other models, such as other algorithms, such as support vector machines and gradient boosting trees. Now I'm going to talk about two more things and then I'll stop. How do we evaluate the performance of these algorithms? We have developed a model. How do we know it's a good model? It's a very simple exercise. You compute the loss function for each algorithm for both the training data and the cross-validation data. And then you plot the loss of the training and the cross-validation for the different algorithms that you've used. And this is one way, a simple way to plot the loss functions. The other way that the computer scientists use is to compute something called the ROC curve, the receiver operating characteristics curve. It's a big name. It's very simple. What they are plotting is the true positive rate and the false positive rate. And you want your ROC to be above the 45-degree line. In fact, you want your ROC to be, who knows, more than 90%. You want the true positive rate to be as high as possible compared to the false positive rate. So that's how we evaluate how good the algorithms are in generating a model that predicts whatever you're predicting. Now, how do we interpret these models? That was a great question in the chat. The way you interpret these models across the different algorithms, because we are using neural net, which is not visual. We're using decision tree, which is very visual. How do we interpret these models? You can use something called these partial dependence plots, PDPs. So what are partial dependence plots? They either take a single variable and show the nonlinearity, or take two variables and show the nonlinearity. So in this graph that I'm showing you here, what is being predicted is the probability of turnover. And I've shown you only two variables of interest, the training performance and the tenure at this firm. Now, as you can see, the logistic regression doesn't show any nonlinearity, but the random forest shows the nonlinearity very precisely at 6 months. The neural net actually doesn't do that good of a job in showing the nonlinearity, at least in our application. So I think Maciej said this, and I'll repeat it. You have to repeat the prediction exercise using multiple algorithms and see whether the pattern, the nonlinear pattern you identified, is robust. So I'm going to skip. The only thing on the takeaways I'm going to say is that there are no confidence intervals here. Nothing should be interpreted as causal. It's just inductively trying to look for nonlinear patterns in the data. I have a different SMJ methods paper, a second paper, where we show the use of supervised machine learning algorithms in the case of facial emotion recognition. So what we did is we took the advantage of a very large data set of CEOs who were interviewed by researchers, and then we used the supervised machine learning algorithm, which predicts the facial emotion on every frame of every video. And the way they're predicting, if you're asking me, what are the factors or the variables used to predict whether you're happy or sad, it's things like the curvature of the lips or how large your mouth is. So a team of researchers have already created the training data set predicting or assigning sad or happy or angry, and then the model is being developed based on a neural net, a convolutional neural net in this case, using those factors such as the curvature of the eyebrows, the curvature of the lips, how large the pupils are, and so on and so forth. And we use that to predict the facial expressions on our CEOs. So I also welcome you to read that other paper. So that's all I had to say, and I'm looking forward to Ariana's presentation. Thanks again, Elena, for inviting.
Again, thank you very much. Thank you very much, Raj. Again, wonderful presentation. I feel I am learning a lot in here. So again, I encourage you to keep on talking in the chat. And now I'm going to pass the torch to Ariana, who will talk about the topic model. So also a little reminder. So please, if you are not the speaker, make sure you have your mic muted so we avoid like interruptions. So Ariana, please go ahead.
Can you see my slide?
Yes, all good.
So Ellen and Anne, thanks a lot for organizing and for the invitation. And Maciej and Raj did a great job. So now I'm going to narrow it down even further. And I am going to talk to you about natural language processing in particular. My name is Ariana Marchetti, and I'm an assistant professor in the Strategy and Entrepreneurship group at London Business School. And I'm very excited to talk about this topic because I use it a lot for my own research. So it was a nice opportunity to just like map it out a little bit. If I think about one of the last slides that Maciej showed about where does machine learning sits in this process of theorizing, creating variables, testing, supporting our research, what I will tell you about in the next 15 minutes is mostly about creating new variables. So how can we use machine learning, in particular unsupervised machine learning, and in particular dealing with text data to build variables. So this is pretty much what we are going to do. As I said, I will focus on unsupervised machine learning, mostly because, well, Raj has already given us a good overview of the supervised bit, but also because when we think of text analysis, unsupervised learning is also where a lot is happening. So I thought of like focusing there, and I use it a lot for my own research as well. All right, so first thing first, what are we trying to achieve? When we have these large corpora of text, we want to analyze them and we want to perform a dimensionality reduction exercise, right? We generally start with a text document, which is a list of words, and this list of words generate their meaning based on their unique order. But these documents give a lot of information. They're highly dimensional. So if we look at these two documents here, A and B, we know that they are different. We can immediately capture it, but what we want to understand is how they're different. And so basically what we want to do is we want to go from all this information to something that is much more parsimonious, we can process and we can put into some constructs of interest for us. So the objective, if you see this funnel, is to go from a lot of text, a lot of words that convey their meaning based on their context and their order, into something lower level, lower dimensionality that conveys some relevant concepts and categories that we can use in our research. This idea of dimensionality reduction, however, is not new. This is what qualitative researchers have been doing for a long time with manual coding, right? Imagine what they did was, they still do, is to read through each document that comprises their text corpora to flag some specific concept and categories that were of theoretical interest, and then skim through this whole corpus to identify some shared categories across different people, across different pieces of text. Now, what's happening though is that this amount of documents, the amount of text data is really exploding. We are seeing companies, individuals producing larger and larger volumes of text that we have available both for companies to run their business, but also to us as researchers. And so the manual coding, it's becoming unfeasible for two reasons. The first is like, we don't want to spend our life reading text. And also for large corporate, it really becomes prone to error. And second, this kind of like top-down manual coding approaches really depends heavily on the researcher pre-existing knowledge of the research context. And this is something that I think is quite interesting. If we want to uncover new theoretical constructs, new patterns in the data, unsupervised machine learning for text analysis can really be useful. So the idea is to basically try to perform the same exercise of dimensionality reduction in large text corpora using an algorithmically assisted approach. So I will start with this general umbrella term of algorithmically assisted, but please notice that using an algorithm doesn't mean necessarily to use machine learning. There are solutions, like for instance, the traditional dictionary-based methods, which are not machine learning based. Those are based on some rules, if then, which are, as Maciej was saying at the start, that's not machine learning. I have coded some rules, like if I find these words in the text, then I will code it in a certain way. What we want to focus on is the machine learning realm of things for natural language processing. And we can do this in two ways: supervised machine learning and unsupervised machine learning. And I'm going to briefly touch upon the three of them, but we will focus today on unsupervised machine learning. So dictionary methods, very simply, how do they work? We want to study a particular construct of interest, for instance, whether firms are talking about innovation in their annual reports to stakeholders. So what we do is to start with a list of words, seeds, keywords that we believe convey this idea of innovativeness. And then we simply go and count how many times the text we have available is mentioning these innovative words. Now, there is a couple of problems with this approach. The first is that it's not context aware, in the sense that we're just going to look at the appearance of these words, but we're not looking at the extent to which these words appear in a certain context, and the context can really change the meaning of words. And second is really heavily dependent on your judgment. You have created the dictionary, you have decided which words are important. If you ask another person, well, they might identify a completely different set of words. So this kind of like hijacks a little bit the replicability and the objectivity of the method. When we talk of supervised machine learning, on the other hand, the idea is that we want to classify text based on pre-labeled text. So as for the paradigm that Maciej and Raj discussed, we always want to do cross-validation, splitting the data between training and testing. So what we do is we label our training data set. For instance, we want to understand whether firms are talking about purpose. So we would have some human coders coding every paragraph, for instance, in an annual report, trying to understand whether the firm is describing purpose-oriented activities. And then we will use this training set to train our algorithm, for the algorithm to understand the patterns, the associations of words that are such that this piece of text is in fact associated with a description of purpose. And then we will feed the new unseen data, the test data set, to the algorithm, so that the algorithm can predict, based on the data that has been learned already, whether the new unseen data are in fact talking about purpose or whatever construct you want to talk about. So in the context of natural language processing, supervised machine learning is really helpful when you already have a clear idea of what specific construct is interesting for you. You want to study innovation, you want to study purpose. Well, you label your data based on what you want to observe, and you want to understand whether this is appearing in unseen data. However, there is a lot of cases where you don't have a clear idea of the specific theoretical constructs that you are expecting to show up in this text data. And this is when unsupervised machine learning is really helpful. And I'm going to talk particularly about this to complete the overview that we're getting today. So I'm going to briefly talk about two specific applications of increasing level of complexity and therefore also interpretability in a sense: topic modeling and embedding models. This is going to be the focus of the next about 10 minutes. And then I will also clarify how we have been seeing an improvement in the application of dictionary methods. This is something I've been seeing in a lot of papers I'm reviewing. Embedding models are being used to enhance dictionary approaches to reduce exactly what I was mentioning before, the lack of context dependence and the subjectivity of this method. So basically you use an embedding model to expand the dictionaries that you can create. So in the next about 10 minutes, I will talk to you about topic models and embedding models. And what I want you to retain is basically a primer on what these models do at a very high level. We don't have the time to go into the details, but also understand how we can use the outputs for research in management. I will start from topic modeling, which is something I've used a lot in my research. And I will give you an example from my own research where I try to measure organizational culture using text that people write about their companies. People write reviews about their companies and post those on Glassdoor. So I'll quickly show you how the data generation process works to help you understand how topic modeling can help me reverse engineer this mental process. So let's say a person goes online and they want to write a review about their firm. The first question they would ask themselves is, okay, what are the topics when I think about my organization that really matters to me and I want to share with the audience online? And the second question is, okay, once I have identified the topics that matter to me, what are the words that I want to use to describe each of these topics? And then the person posts the review online. Now, say that I want to use this set of reviews that have been posted online over time to do some topic modeling to measure culture. I will show you in a second how to do that using a topic modeling algorithm. I would first compile all these reviews for the specific firm in a unique corpus, and then I would feed the corpus to the topic modeling algorithm. The algorithm does two things that helps me reverse engineer the mental process of creating the review. First, it estimates topics. So in a sort of clustering approach, it identified words that are more likely to appear jointly across the reviews, across the documents than other. This list of words that are clustered together statistically are the topics. And second, for every topic that has been estimated and for every review, the algorithm tells me which percentage of the review is talking about the topics. So basically, out of the topic models, we have two outputs that we can use for research. The first is a topic word matrix, where every row is a topic and every column is a word that is being used across the corpus, so in the vocabulary. And every row tells me how likely the specific word is to belong to a given topic. So what I can use this matrix for is basically by looking at the top words that are likely associated with each topic, I can find some coherent meaning and I can interpret the content of the corpus, because keep in mind that the algorithm is not going to do the interpretation for you. This is something that you have to do ex post. And then we have a second matrix, which is called document to topics matrix, where every row is a document, in my case, a review on Glassdoor, and every column is a topic that has been estimated by the algorithm. And so every row tells me which percentage of the document is covering each of the topics. And the idea is that people, when writing about reviews, can talk about different things, can be more or less focused on different topics. So now, just to give you an example on how these two matrices can be used to build variables, I give you an example from my own research on how I use these two to measure culture. So the main matrix I use in my own research is the documents over topics, basically the distribution of every review over the topics, which I think gives me a very nice approximation of a firm where people have a distribution of attention to different topics that characterize the firm. So the thing I do first is to just look at this matrix without interpreting the topics and basically compare the distributions of attention over topics across people. And what I learn is whether people are talking about similar things, whether they're focusing on completely different things, and whether they have these spiky distributions, meaning that they really care about one topic only, or rather they talk about a lot of different things. And this to me gives me an idea of what I call cultural strength, is how homogeneous the culture of this place is. And the second thing I do is using the, sorry, there's a typo, the words over topics, the topics over words matrix. I interpret the specific topics that the algorithm generates to understand the content of the culture, specifically which values and norms are people talking about when reviewing their companies online. So just as a quick example, you can see, for instance, we can compute individual similarity. So we can compare every person in the way they describe the different topics to other people and understand whether people are in this organization on average similar or not, and whether they are focused on describing just a few topics, as we can see for review number 4, or they're rather talking about a bunch of different things. And then by looking at the top words that are associated with each topics, I can also interpret those and try to get an understanding of the content that people are talking about. So this was just like from my own research, a very quick overview on what topic model does and how you can use the output to build variables. I gave you the specific example of culture, but I mean, I will have a slide at the end. You can use it in very, very different contexts, disentangling the content and the configuration in the same way. And then I want to briefly touch upon word embeddings, which is the later generation of deep learning models. And if we think of all the large language models revolution, well, word embeddings like BERT are already large language models. The main difference with the current generation of large language models is the size of the number of parameters, right? Here we are talking about order of million parameters, and ChatGPT, we're talking about order of billion. So the size of the model is significantly different. Now, the main difference between a word embedding and a topic model is that the word embedding really keeps into account the context where a specific word is used. If you remember, at some point I said, well, if you use the same word in different contexts, it can mean very different ways, very different things. And word embeddings are really good at that. Basically, the idea is that they want to predict a certain word in a sentence based on the other words that surround the target word that you have. So the basic idea is that you want to get into a vectorial representation of every word in your document so that the context is relevant and words that appear in similar contexts are close to one another. And at the end state, you will have a highly multi-dimensional space, generally a 300-dimension space, where you can position all these vectors in the space, and you can perform some computations to understand how far away words and documents are from one another. Now here, talking really about practicalities, what's really important for word embeddings is how you choose your training data set. If you have a very large amount of data, the ideal state is always that you use your own data to train your own embedding models, because in that case, the context, the word context is really relevant to your specific setting. But in case you don't, there are many, many tools available where you can use pre-trained models on general purpose text, like for instance, all the Wikipedia articles or all the news repositories and so on and so forth. So this is an important point to keep in mind. Here it's an example from a very nice paper published in 2019 in ASR, where basically the authors use word embeddings to understand the change over time in the meaning on how some words are used, the meaning that is associated to some words. So as you can see, the main output of these word embeddings is a space where you can represent every word or even every document in a sense in this space, and you can do some algebra and basically understand how far away different words are, different documents are from one another. As I said, embedding models have been used more and more to enhance dictionary methods. So the idea is that if we go back to this representation, imagine that you have created your initial seed words. What you would do is you would represent your seed words in the embedding space, and then you would take all the other words that appear in a cloud that is proximate to your seed word, so that you have more context dependence and also less subjectivity in the generation of the dictionary. I've been seeing this in many of the working papers I've been reviewing. I think it's a very nice way to kind of re-enable an old method with some support from machine learning in a sense. I wanted to conclude with a couple of things. First is when to use each model, and second, the pros and cons. So topic modeling are really simple. We go back to the idea of trading sophistication, predictive accuracy, and interpretability. Topic modeling are really simple models that produce a relatively sparse output, meaning that they're much easier than word embeddings to interpret. I like them when I need to get a granular understanding of how the documents are distributed over the topics. And I don't know the specific theoretical constructs that I want to focus on a priori. I let them emerge from the bottom. But I also need to have a clue about roughly how many topics am I expecting to estimate from this corpus. We didn't have time to talk about this, but this is one of the parameters you have to choose for topic modeling, and it's basically would have been another 20 minutes of conversation pretty much. On the other hand, word embeddings have the advantage of keeping the context of language into consideration. I think though, because they're much harder to interpret, they're good to use when you don't have any specific interest in the text content in general, but you want to focus on specific theoretical dimensions that you might know ex ante, and you're mostly interested in grasping the geometric proximity of these theoretical constructs. And also, you don't need to know how many relevant dimensions you need to estimate the models. This is something that I want to mention because I've been working with this quite a lot. And so the burden is pretty high in these methods with validating your theoretical constructs and in a doable and convincing way. When you don't have a way for doing that, well, always remember that there are other methods that we shouldn't discard, like traditional dictionary survey, search and survey approach. So keep in mind that you have to have large enough data and an ability to validate your constructs to be able to use these approaches. And finally, pros and cons. I think the main pros of unsupervised machine learning for natural language processing comes from the scale of the data, both within and across firms as the unit of analysis, in my case. In this case, you can reach much more representativeness and generalizability of your studies compared, for instance, to survey studies. And I really like this last point about you have a bottom-up way to uncover new theoretical constructs that might have been underexplored in prior research. If we think of the cons, though, well, it's very hard to parse out noise from the data, and especially if you go to fancier and more predicting, better performing models, it gets harder to understand how to calibrate and interpret the findings. And as I was mentioning, you really need to have a good strategy for validate both the models and the theoretical constructs with a high bar for publication. I'm happy to explore this more in the roundtables and breakout rooms later, but well, sky is the limit, I think. I gave you the example of culture, but there is really a lot that can be explored with this. Pretty much, I would say, wherever you have a language construct that can be signified with a set of words, so pretty much always. I think it's very interesting to understand attention direction, cognitive frames, but also at a higher level of analysis to understand categories at the product and market and industry level, and to explore the evolution of domains like technology or science. This is it from me, and thank you so much for listening.
Thank you so much, Ariana. Again, this was an amazing primer on both topic modeling and word embedding. So thank you so much. I feel like I'm learning a lot right now here. So I'm very happy that we organize this panel, right? That's a huge learning opportunity. So I feel we are running a little bit over time. So what I would suggest is, first, for the posterity, let us do a screenshot. So please, I would love you if you could put your videos on. So we do the screenshot to enshrine this moment in the history of SMS. Okay, and after that, perhaps we can take like one question, and then all other burning questions that you have. I actually encourage you, you can stay, and I think we still have a bit of space in the breakout rooms. So if you have some burning questions, you can still ask them in the breakout rooms. Okay, so let's do this. So please put your videos on. Smile and say NLP. Okay, I think that was a good one. Okay, perfect. We have this moment captured now. So yeah, as I said, I think we are running a bit over time. So I would love actually to pick on the question from Deepika, because I think it's kind of pretty high level, and it would be great to hear the thoughts of all panelists on that. So Deepika was asking in general that, well, a lot of these methods typically imply some kind of ex post theorizing. So how accepted this method would be when you think about publishing in strategy or theory. So what are what would be your thoughts on that? How accepted it is? Any tips you could suggest for people who use these methods to kind of pass any hurdles? So maybe you can actually go like in the order of presentations, Maciej, Raj, and Ariana.
Yeah, I mean, so I think for this question, you kind of have to really ask, I mean, which one of the tools, right? Because the machine learning is such a huge, bag of tools that, which tool would you use? Which tools can you misuse? And I think the misuse of those tools, it really depends on kind of how do you use them. I mean, just to kind of give you the space, I mean, you can use, for example, machine learning to deal with missing observations, right? So sometimes, for example, the methods with missing observations is that let's say if you had some kind of variables, you would choose like a mean of the entire sample to replace, let's say, a missing observation. You can actually train a machine learning model to predict much better based on the other things that are still there. How much how much data can I put in there? So the applications kind of, range from a very practical, very easy, where it's really hard to think that you can sort of misuse the tool, Again, if you're just trying to predict something which is not theoretically relevant, like a variable for your theory, as long as you do a good job predicting it, there's no kind of a reason to be sort of worried other than, some kind of a measurement error, that, you're doing something kind of shady in terms of theory. I think that where a lot of people kind of start to get a little bit uncomfortable is when you're using machine learning tools to peek into the complexity of the sort of observable world, where let's say you have a huge data set and you unleash those machine learning models on it and they find lots of weird relationships. So then you kind of go and start to hypothesize, I wonder why this is. And then you proceed to test those hypotheses using exactly the same data that you unleash those machine learning tools on. I mean, of course, that's kind of a problem. And I've put a paper by Shrestha and co-authors that actually talks about, kind of, let's say, a legitimate way of using machine learning tools to theorize. You have to be very careful, and I think some good understanding of the the philosophy of science, how we sort of use those models, what's inference, what's prediction. It really helps a lot. So I would invest some time into understanding sort of the underpinning logic behind all of those models, because unsupervised, supervised, what do we use them for in our sort of research are really, really key. And in many applications, no problem, no worry. But sometimes, when you sort of start to touch and hypothesize and test, you have to be careful what you use those tools for.
So I can add to that, Elena, because you wanted us to go in order. So I think I agree with Maciej that if the two big sort of like high-level practical way to think about this is the use of machine learning methods is to either construct new variables or to find new patterns in the data. So I think both of these jobs need to be done well. So all the caution we pointed out in terms of making sure that the constructs are and the patterns are robust across using multiple of these methods is still salient. But if you are, for instance, using supervised machine learning methods to find new patterns in the data, then that is pure induction. And then you can find a new pattern like I described, that the probability of attrition is more or less before and after the first 6 months. Then you can, in a second study, run a randomized control trial to establish causality of that pattern. But the one thing I'll add here is that I think the strategy field, and I'm probably okay saying this, is now very open to inductive papers. So I've sat through many Meet the Editor sessions, and I've heard people like Rajshri Agarwal and Alfonso Gambardella talk about how the field of strategy is very open to exploratory papers, or what Will Mitchell, who's actually a former editor at SMJ, he called them the red state papers, where you are in a very inductive fashion, you are trying to generate a pattern in the data, which is an important pattern given a new phenomena. So I think the field of strategy is probably very open to those kinds of papers, and that goes beyond, of course, the use of machine learning to find those patterns.
Yeah, so Ariana, would you like to add?
So I would like to briefly add specifically on the construction of new variables, which is what I do mostly in my research. I think the two main burdens in the review process are the validation, both on the specific model. So are your variables stable to using different hyperparameters and different way of tuning these models, but also phase validity, because very often we are trying to measure all constructs in a more reliable way. So in particular, in my case, for instance, I'm talking to a long-standing tradition of cultural research where the burden is on me in squaring my results, my way of measuring this construct with old ways. So I think it's really important that you put a lot of effort ex ante. I would say already, like, it's not something that the reviewers should solicit. It's something that should come already ex ante, showing the phase validity of what you're measuring, and why you are not reinventing the wheel in a sense. So it's really important that you showcase what we are learning that is new, what kind of issues we are solving by using these fancier methods over simpler empirical approaches. And also something that was prompted by one of the comments in the chat, I think it's important also to explain why we use certain models or certain approaches, certain models over others in computing our variables. So it's important that you gain a very good understanding of what are the pros and cons of different algorithms, different models, and how they best fit certain research questions and certain data sets.
Thank you so much again. I would love to give a huge shout out to Ariana, Maciej, and Raj. Thank you very much for providing these excellent overviews of different methods. I think we all learned a lot today. This session has been recorded, and the recording would be available on the SMS YouTube channel and on the SMS member circle as well.